just forgot that I didn't push the record button. So now we're recording. So, and it looked like the stream kind of messed up anyway. So for whatever reason, I don't really know. It's fine until I start actually streaming, and then it acts crazy. So there's something else going on, but we'll worry about that later. What we're going to do is we're going to talk about power transmission. So a few days ago, last week, we talked about torsional shear stress. So in a circular shaft, you apply a torque to it, and there's a shear stress in there that could be large enough to break, fracture the shaft, or maybe just twist it to the point that it yields. So we calculated that shear stress. We actually derived how to develop that shear stress equation. Then we did an angle of twist. So maybe it doesn't yield or break, but it twists the shaft a little bit. And so we want to know how much does it twist, because that could be a failure mode. Now we're talking about just the shaft is spinning and it's transmitting power. So there's some kind of power source, a motor, engine, something like that. It's connected to a shaft, and then that shaft is delivering power out to some other elements. So maybe there's gears, pulleys, belts connected to it that are delivering power to other parts of this machine or a building or whatever it might be. And we want to calculate some of this power transmission capability. So that's our topic for today, is power transmission. I'll do a little bit to derive how power transmission is going to be calculated in a shaft. We're going to stick with circular shafts. It is possible that you would do some other shape, like hexagonal or whatever, but we're going to do circular. Again, that goes back to this idea that when we did the polar moment of inertia, we were deriving the equations for polar moment of inertia based on a circular cross-section. So we're going to keep these as circular shafts. If you have a prismatic shaft, then those edges, the corners, would create some kind of stress concentrations that we're not accounting for. So, not green. Let's write in this color. There we go. Power transmission. So we're transmitting power from one place to another through some kind of circular, either solid or hollow. That part doesn't matter. But this shaft. We're actually going to start with a regular looking thing here. Got a box. Well, let's make it that way. Let's put a force on this box so that we can push it, to the right here in our picture. So it ends up over here. Make it the same kind of box. I wonder if we can get it to, it's fine that it's, we'll do this. There we go. So we've moved this box from, let's just say from here to here, some distance d. So we have an equation for this from a long time ago, back in physics somewhere, that work equals how hard I had to push, force, times how far I pushed, distance. So that's F times D here in this picture. We also know, since we're talking about power transmission, power equals that work that we did, but how fast did we do it? So work divided by time. So which would be force times distance divided by time, right? The only thing is that we're not sliding a box on a frictionless surface here. We're rotating a shaft. So let's look at this same idea, but applied to a circular shaft. So let's get us a circle, make a big circle. There we go. And let's take, oops, get off of there. Some point, this will just be some point on the circle here that we've got, and we're going to apply a force to it. So there's our force, and that point, when we apply the force, maybe this force is applied with a coupler that's connected to it, or maybe it's a belt or a gear, some kind of pulley, somehow we're applying this force to make the circle, which is the cross section of the shaft, make it spin, and so that point moves from position 1 over here to maybe position 2 up here. So it traveled, this distance. So that blue line I just drew, that's this same, idea of the blue line up here, D. So this will be a distance. We didn't actually translate the shaft necessarily. We just rotated it about its own center. And we rotated it through some angle. Let's use that green for that. So some angle, we'll just call it alpha. I don't want to use theta here because it's not the theta that we used before where it was angle of twist. We're not talking about twisting the shaft. It's freely spinning through this distance. It is also possibly twisting, but we're ignoring that for thinking about this power transmission idea. So the distance here is an arc length, right? So if we had, let's do a blue, R is the radius of our circle. So the distance equals that radius, R, times alpha. Alpha is the, the arc, well, the angle of the arc from point 1 to point 2, how far we rotated the shaft. So R theta, or well, except I'm not using theta because we used theta as a angle of twist earlier. So R alpha in this case. So we're going to put that in for our distance value. So now we've got work equals force times distance, which is R alpha, and power is work divided by time. So we won't forget that, but this is important. Let's take out our parentheses here. So this force times R. So I'm assuming this force that I drew is perpendicular to that radius, it's tangent to the circle. Force times a perpendicular distance is a torque. So if I collect those together, I can write it again as work equals torque times alpha. And then I'm really interested in power. Power is work divided by time. So power equals torque times alpha over time, some number of seconds maybe. And this alpha in radians, that wouldn't necessarily be a degree angle, but this radian per time, a lot of times it is theta, but again, I'm kind of avoiding theta because of the use we already used theta for. So if I did power equals torque and kind of separate out alpha, which is normally theta here, but again, we're not doing that. Alpha per second, where alpha is in radians. Radians per second is angular velocity. So this term, let's kind of isolate it. This term, radian per second equals omega equals angular velocity. So now I have an equation. If I take all of that and rewrite it as a clean equation, I have power equals torque times omega. So that is our power equation for a shaft that is rotating versus power in a sliding block. But that's where we derived it from. So you'll see this P equals T times omega. It's not W, it's an omega angular velocity. So the units in that will be, torque will be something like inch pounds, omega radians per second. So I'll get units that are something like inch pound per second, or maybe foot-pound per second. You might get Newton meter per second. A Newton meter is also a joule, so you'll get joule per second. You won't immediately get horsepower. So a lot of times when you think about a shaft rotating connected to some kind of engine, you're thinking horsepower. How many horsepower does this motor rated at, or something like that? So horsepower is not quite exactly like one of these, but you do see it a lot. So we do have to talk about what horsepower equals. So a horsepower is 1 horsepower equals 550 foot-pounds per second equals 6,600 inch-pounds per second. So you just have to remember those conversion factors. Eventually you'll have to think of them to convert between the equation, what the equation actually generates, inch-pounds per second or whatever, and convert over to foot-pounds. Or, well, foot-pounds per second being a 550 foot-pounds per second being a horsepower. Another set of units here that radians per second. So also omega is radians per second, but when you're talking about how fast that engine is spinning or what's the speed of that shaft, you usually, at least in the US system, don't talk about radians per second. You talk about RPM, revolutions per minute. So we do need to be able to also convert radians per second over to revolutions per minute. So a revolution per minute would equal 2 pi over 60 radians per second. So you need to convert the minutes and seconds, and you need to convert the revolution, being a whole circle, into 2 pi. So 2 pi over 60 radians per second. Hertz in the metric system, you may not see RPM. This is equal to RPM. You might see the idea of hertz. A hertz, maybe if you've heard of that one before, it was in an electrical setting, and it's talking about the frequency of the power source. So you might have seen it there, but hertz in general just means cycles of anything per second. And in here, the cycle is 1 revolution. So 1 revolution per second. So it already is in the second unit, like radians per second. So you just need to convert the revolutions over to radians. So that would equal 2 pi radian per second. So you multiply by 2 pi to get from radians per second to hertz. All right. So let's do a little example here of what this might look like if we put it in context of an actual problem to solve. So let's just say that we're, given a little motor. We'll just make it an electric motor of some sort, and it'll have a shaft, and it has delivering 5 foot-pounds of torque, and let's call it a 5 horsepower motor. We'll put it some little stand for it to sit down on. So it's bolted to the table somewhere. Okay, and we want to see how much power this thing represents. So, well, we know how much power. Knowing that it's 5 horsepower, what speed is the shaft turning? So, find the speed of the shaft. So we're making a couple of assumptions. Some of the problems that you run into might say something along the lines of they are the motor, the power transmission is so many percent efficient. We're assuming right now that it's 100% efficient. We know that's not true. No energy conversion process is 100% efficient, but at least no mechanical one. So we're going to assume that it is, though, for now. If the problem specifically says something about this process or this transfer being 80% efficient or whatever, then we'll deal with that then. But most of these problems won't mention efficiency, in which case you assume it's 100% efficient. All right, so we've got this little setup, and we know that power equals torque times omega. And let's just fill in what we know. We know, again, assuming the 100% efficient system here, that we have 5 horsepower equals 5 foot-pounds of torque times omega, which is going to be the speed of the shaft, not in RPM, but in radians per second. So let's see if we can convert. We can't just MathCAD. We could probably just plug these things in, but this time I'm going to work this one out by hand so that we can see the conversions. But 5 horsepower, where 1 horsepower is equal to 550 foot-pounds per second, equals 5 foot-pounds times omega. So that'll get me out of horsepower and change the left-hand side over to foot-pounds per second. So 5 times 550 is 2750 foot-pounds per second, equals 5 foot-pounds of torque. That's how much it's delivering, the little red arrow there, times how fast the shaft is spinning. So we want to know how fast this shaft is spinning, so we've got omega equals, let's see if we do the move the 5, divide by 5 foot-pounds, I guess. We've got 2750 divided by 5 is 550. Yes, I think that's right. I need to get a calculator. Maybe I should find one. I don't see one handy. I think that's right, 550. The units on that would be, I took foot-pounds per second and divided by foot-pounds. So I end up with radians per second, right? 550 radians per second. Most of the time, you want these not in radians per second. You want them in either hertz or revolutions per minute, RPM. So let's see if we can convert 550 radians per second into RPM. So we want, instead of seconds, we want minutes, because RPM is revolutions per minute. So there are 60 seconds in 1 minute. So that'll get us radians per minute. We don't want radians, but we know that there are 2 pi radians in 1 revolution. So now we'll have revolutions per minute if we do this math. So 550 times 60 divided by 2 pi. Really don't know that. Let's see. Here we go. Oh. Let's break out the old calculator. All right, so we've got 550, and we need to multiply by 60. We need to divide by 2 and divide by pi. Where's pi? Well, 5250.1. 5250.1 RPM, revolutions per minute. So 5,200 RPM, which pretty fast, you know. But that's how you would go through and use the power transmission equation to back out the missing variable here. So you can be missing one of these. If you know the torque and the power, you can find the shaft speed. If you know the shaft speed and the torque, you can find the power. And if you know the power and the shaft speed, you can figure out the torque. All right, so that's the basic of one of these. Let's look at some web work and work on one of those. And maybe I'll do this one in MathCAD. Let's see. So here's optional 3, problem 7 is it says simple horsepower. doesn't even have a picture. Determine the horsepower that a 7-inch diameter shaft can transmit at 190 RPM if the maximum shear stress in the shaft must be limited to 11,500. So this is sort of a design problem. They've already given us the allowable stress, shear stress for this particular shaft, where we're going to have to use our power equation to figure out how much torque it's dealing with, and then our shear stress equation to figure out how big it needs to be to deal with that torque. Without, it doesn't give us, factor of safety. It's just built into this 11,500 number. All right, so let's go over to, well, let's write it out first, then we'll drop it in MathCAD. All right, so we're given, it actually tells us, what are we trying to figure out? Determine the how much horsepower. We know the size of it. I said that wrong. 7-inch diameter. This is a massive shaft. 7-inch diameter. All right. It doesn't say anything about an inner diameter, so we're assuming it's a solid piece. It doesn't say what material. They just give us the tau allowable equal to 11,500. So based on that number, that is some kind of steel with a factor of safety applied to it. So this is a really big steel shaft spinning 190 RPM. And we want to find max power. And again, this one doesn't mention any efficiencies or anything like that. So we're going to assume it's all 100% efficient. All right, so let's see what we need to do here. First, power equals torque times omega. We don't know how much torque it's delivering. We know the power and the speed, though, so we can figure out the torque. So, no, we don't know the power. We know the speed. Oh, we've got to go the other way. So, tau allowable equals T times C over J. So we can get the torque from here because we know the tau allowable and we know the size of it, so we know C and J. So we'll start here and then plug this into the power transmission equation. So 11,500 pounds per inch squared equals how much torque is in this shaft. So that's how much the maximum torque that can be in the shaft. So let's put tau max. C is the outer radius. It has a 3.5-inch diameter. So, it has a 7-inch diameter. So 3.5-inch radius. Pi over, we'll do 32 times D to the 4th, which is 7 inches to the 4th. Okay, so the only unknown in there is tau max. So therefore, or not tau max, T max. T max equals, and we'll have to do some calculating. So let's put this guy in MathCAD. Where did I put MathCAD? There it is. All right. 11,500. That was PSI. Control equals T max. We'll go ahead and max in there times C, which is 3.5 inches, over J, which is pi over 32 times diameter, outer diameter, 7 inches to the 4th. All right, so let's see if we can get this guy to solve for T max. I think there. We might have to do this one manually. Sometimes this MathCAD Prime is really slow at solving. It did pop it out there, but it gave us some weird units, inch cube PSI. Not sure why it decided that's the correct unit, but let's convert those over to, see, can we just do times? Or can I convert them? Can I just tell it I want it in foot pounds? Here, let's copy this thing. And then sometimes this one doesn't really have a unit placeholder. Foot pounds. Well, that unit would be inch pounds, wouldn't it? So this is in inch pounds. 774,000 inch pounds of torque. That's a lot. All right. Let's go back over to see what we need to do next. So we found Tmax was, oh, I forgot the number. 774,500. 774,500 inch pounds. All right. So now we can take that number and plug it into the torque that we're delivering in this power equation. So we know the power was, no, we want to find the power. We know the speed, 190 RPM. So power equals this giant number, 774,500 inch pounds times speed of 190 revolutions per minute. Now, you can't just go, if you're on your calculator, not MathCAD, you can't just go multiply these two numbers together because you'll get 774,500 inch-pound revolutions per minute, which do not translate over to any kind of power. So we do need to convert these correctly to get radians per second out of the 190 revolutions per minute. I'll do that over here, and then we'll just let MathCAD do it for us. So revolutions per minute converted to radians per second, I got to get one revolution is 2 pi radians, and 1 minute is 60 seconds. So that will give me radians per second if I needed to convert it manually, like on an exam or something. But let's see what MathCAD can do. All right, so let's just say that T equals that. Oh, now it will recognize that as a unit. Power equals T times omega. It doesn't know omega yet. Omega is 190. Is RPM a unit? Yes. All right. And then let's see what this equals. Now, it gave it to me in watts, which is also another unit of power for the SI system. I didn't think about that one, but when we're writing down all the units. But watts would also be another system. This problem wants horsepower, so let's just, I don't know if it's capital H. No, it's lowercase. So 2335, let's put some more decimals because you know how web work can be. Let's make it a decimal number. There we go. So let's put this over in here, 2334.856. And sure, correct answers in case we got it wrong, but we got it right. So that's a relatively straightforward one, but it is, you do have to do two different things. You have to deal with the shear stress and the power transmission. Let's do another one. Here's another one with no picture. A lot of these don't, I mean, the picture doesn't really tell you much because it's just a picture of what I drew, like the little motor with a shaft coming out of the end of it. Solid steel. So this one, they give us a modulus of rigidity for that. We don't need to look it up. 3-inch diameter, so not as big as last time. Must not twist more than 0.6 radians in a 22-foot length. Determine the maximum power that this shaft can transmit at 260. So this is a similar problem, but they are, instead of limiting us on shear stress, they're limiting us on angle of twist. This time I want to copy this so that I don't have to keep looking back and forth. Oh, wait, that's, well, I guess we can just do it in MathCAD, can't we? I just dropped it straight into MathCAD, so let's just try it over here. All right, so let's say G is 12,000 ASI. Whoops, I erased it. There we go. OD equals 3 inches. So you could just lose lowercase d, but this one doesn't have an inner diameter, so it doesn't need the OD part to distinguish between the two. Must not twist more than 0.6 radians. So theta max, let's do theta max. Max equals, got some ellipses in there, 0.06 radians. L is 2 feet, so that's the length of the shaft. So that's a relatively long but a large diameter steel shaft. But this would be something maybe like in a directional drilling machine, something like that. Uh, maybe, yeah, it could be even longer than this. I don't know if that would be a solid shaft though. It would be coupled together. Um, Maximum power that the shaft can transmit at 260 RPM. So we know omega is 260 RPM. Okay, so those are our details. So we need to go to our angle of twist equation and figure out what the torque is. So let's do, let's see, do I want to do the variables? I'm not sure how well this MathCAD will work with this, but we'll try it out. Theta max equals T max times L over J, which we'll have to define J here in a minute, times G. Okay, so let's define J. It's solid, so it's pi. I've been using the pi over 32. If you use pi over 2, then that's radius to the fourth. Pi over 32 is diameter to the fourth. Let's see if this guy will solve for T max. It doesn't solve for T max. Or are these the right units? Let's see. So these should be actually just radians in the end. I've got KSI inch to the fourth feet. So that will give us pound, or well, I think that will come out to be 260. Is that 1,000? Oh wow! But the inches to the fourth over feet. There's some weird. It decides to do some weird units here. But let's see what we got. T max equals that number. Let's see if we can get it to put it in foot pounds. No, not that way. I don't know how to really have a unit placeholder. It's just kind of these weird units. All right, so it's not asking, the problem statement's not asking for that. This, it's actually asking for max power. So now we need to do power equals torque times omega. So we've got T, we've got omega. Again, if you're plugging these into a calculator, you're going to have to convert these units to compatible units to be able to multiply them together. MathCAD will do that itself. So power equals T times omega equals, let's put, it did come out in watts. And then let's convert this guy over to a decimal so that we can plop it in here, 3195.066. And let's see if it likes it. Oh, whoa. That is a lot of horsepower. What did I do differently? Let's make sure I didn't. This could be a conversion problem in MathCAD. Could be. Let's actually do this one by hand, because this could be one of the deals where MathCAD actually works against you. So particularly when there are radians in a unit, it can do some weird stuff by thinking radians and degrees and converting where you don't think it should convert, but it could do that. Let's do this one by hand. I think this is one of the ones where MathCAD actually creates problems for you. So let's actually drop this one into OneNote and do it by hand. So let's see. I've got to get the problem statement again. So we wanted to solve theta equals T times L over J times G. And we had a value for theta of 0.06 radians. We want to solve for the torque that creates this amount of twist. 22-foot length, I'm going to convert that over to inches, so there are 12 inches per foot. J pi over 32, that could be something. Let me check MathCAD, make sure I did that part right. I did pi over 32 times diameter, which is 3 inches. Okay, well, let's keep working. It was a 3-inch diameter shaft, so pi over 32 times 3 inches to the fourth. G is 12 million psi, so 12 times 10 to the 6th psi. So all of those units, feet will cancel out. I should be left with nothing but radians. All right, so let's see if we plug this in to a calculator manually. We get 0.06 radians equals, let's see, 22 times 12, 12 million divided out. 3 to the 4th divided out, pi, and then 32 multiply. So I get 2.767 times 10 to the negative 6 t. Does that seem right? It doesn't seem right. T would be 0.06 divided by that number. Oh, wait, hold on. Oh, there we go. 1, 2, 3. Torque of 21,684 inch-pounds, which is 1,800 foot-pounds. That's kind of high, but it's a 3-inch diameter shaft, so maybe, but it's really long. It's like 22 feet long, so it's going to have a lot of twist in it because it's so long. All right, so the next thing we would do, though, is power equals torque times omega, and we want to find power. The torque, what was the torque? Oh, yeah, I got those weird units. 21,684 inch-pounds times the speed of this thing was 260 revolutions per minute, but for power I want inch-pounds per second, so got the inch-pound part. 1 revolution is 2 pi, and 1 minute is 60 seconds. So let's see if we can do all this stuff. 21,684 times 260 times 2 times pi divided by 60. That's a lot. 590,392.726. That unit set should be inch-pound per second. The WebWork wants it in horsepower, so we would need to divide by 6,600, which is 89.453 horsepower. Remembering that 6,600 inch-pounds per second equals 1 horsepower. And I'm pretty sure that was the number that WebWork actually wanted, 89.53 horsepower. Oh, let's go over there so you can see it. And that's right. Well, we were off a little bit, 469, 453, but WebWork was even happy with that. So this is probably one of the ones that's a little bit of a danger using MathCAD. MathCAD, and it's probably something to do with the radians. I wonder if I just took the radians out of this. No, it still doesn't change it over there. So there's something in there that it is not converting correctly. Pi over 32 d to the fourth. G is 12 million psi. All that looks okay, but there's something in here that it's not converting, or TL over JG. Yeah, something I converted or typed wrong somewhere in there. I wonder if I just leave. Yeah, not sure where it's got a difference at, but somewhere in there it's got something different. And I think it is something to do with the degree, but now I've taken them all out. I actually don't know. I have omega RP. Oh, no, that's right. Anyway, that can happen in MathCAD. I either made a typing error somewhere, which I don't see currently, or it's something to do with a radian degree type of thing. Anytime you have revolutions, but you're converting over to some kind of horsepower, it can do some weird stuff that I'm not seeing the issue with somewhere in there. But when you work it out by hand, you get it correct. Let's see if there's another one that's worth doing. We've seen this picture before, I think, but in a different problem. Let's see what it's asking about. So it's developing 90 horsepower. This one's probably a good one to at least work through, I think. It doesn't have any efficiency associated with it, but still, I think it's probably a good one to try and do. So let's grab this and, put it over here. All right, so it made it really small. Let's see if we can make it larger than that. Make the picture bigger. That's kind of readable. All right, so we've got a 90 horsepower motor. Oops. So 90 horsepower. And it is developing that 90 horsepower at a speed of 350 RPM. So this little shaft here, 350 RPM. And it's transmitting that 90 horsepower at a geared, N1 versus N2 geared down ratio. So N1 is 85 teeth, and N2 is 17 teeth. So whenever you change the speed of a shaft, you also change the torque delivered in that shaft. And again, this problem doesn't mention any kind of efficiency losses, which there would be, but we're ignoring those. So in this case, I have taken a big gear, attached it to my motor, and then that big gear, the 85 tooth, is meshed with a smaller gear or pinion, 17 teeth. And so that smaller N2 is spinning way faster than the big one. For every revolution the big one makes, it goes around 85 teeth. Well, 85 divided by 17 is 5. So that smaller gear has spun 5 times for every one revolution of the bigger gear. So that this shaft is spinning 5 times faster than the green one. And we know how the green one is spinning at 350 RPM. So the yellow one is spinning 5 times faster than that. Simultaneously, it is spinning faster, but it is delivering 5 times less torque. So we didn't calculate the torque yet from the green shaft, but the torque in the yellow shaft is 1/5 of whatever the green shaft is, because it's going 5 times faster. So those are paired together. So if you spin it faster, it delivers less torque than the meshed, the gear meshed shaft. A and B. So gear A delivers 41 horsepower. So we'll, I don't know, do it this way. 41 horsepower. Gear C delivers 49 horsepower. If you add 49 and 41, you'll get the 90 that we input. So if this was a less than 100% efficient system, then I would input 90 horsepower, but I wouldn't get all 90 out. I would lose some of the 90 as heat, friction losses type stuff. Here, it's 100% efficient. We have some lengths. A is 5 feet. B is 8.5 feet. And C is 4.5 feet. So these are pretty long shafts. If the maximum shear stress in all the shafts, so no matter which one, tau max or tau allowable, is 4,000 psi. So that's kind of low. But it is a shear strength, so it is going to be lower than like a yield tensile strength or something. Determine the minimum satisfactory diameter for the motor, the green shaft, the minimum satisfactory diameter for the power, the yellow shaft, and then based on those shafts, the angle of twist between gear B and the 17, so the smaller pinion gear there, pinion. Assuming the whole shaft has the same diameter, which is that smaller minimum satisfactory diameter, and it's made of annealed ENGR. Seems like I've been getting that annealed ENGR material quite a lot lately. All right, so first thing to do, I think, is to figure out how much torque is in the green shaft. So we've kind of already done that problem before, but let's still work on that. So for the green shaft, power equals torque times omega. We have 90 horsepower going in, 100% efficient system, so there's 90 horsepower on the other side of the equal sign. We don't know the torque. We know that it's spinning 350 revolutions per minute. So this one's kind of an exercise in unit conversion. So 90 horsepower, which 1 horsepower, well, let's do it this way. 1 horsepower is, let's do inch pounds. So 6,600 inch pounds per second. So now I've got inch pounds per second on the left-hand side equals torque times 350. I'm going to write it as revolutions per minute times 1 minute is 60 seconds, and 1 revolution is 2 pi radians. So now my numbers on both sides are equal unit-wise, and I can solve for torque. So let's get my calculator out. 90 times 6,600. So on the left-hand side, I've got 594,000 inch pounds per second. Torque times, let's see, on the right-hand side, I've got 350 divided by 60 times 2 times pi, 36. 350 divided by 60 times 2 times pi, 36.652. Those units would be radians per second. So T equals some number of inch pounds. 594,000 divided by 36, that was 0.652. 16,000 206.394 inch-pounds. We're actually trying to find the maximum satisfactory diameter for this green motor shaft. So we know the torque in it now, hopefully. There's the torque in the green shaft. So now we go over to assuming it doesn't mention anything about angle of twist here. Well, it has a calculation for angle of twist at the end, but it says the limiting thing is the maximum shear stress. Sometimes you might have a problem where you have two limiting things. You've got the angle of twist has to be limited to some amount, and the shear stress in the shaft has to be limited to some amount. So you have to check both cases and see which one is the actual limiter. Here it just tells me to limit the to 4,000 psi of shear stress. So tau allowable is 4,000 psi equals T, which we just found, times C, which is what we're trying to find, which is D over 2. We'll just do C though. Over pi over 2 times C to the fourth. So that C and that C becomes C to the third. So let's do some rearranging here. I've got 4,000 psi equals T over pi over 2, 1.571 C cubed. And T, we actually have a value for 16,206.394 inch-pounds. So C, we need to move over to the left-hand side. So take the 4,000. So I've got 6283.18. Those would be PSI times C cubed equals the 16,206.394 inch-pounds. I'll divide that through, and everything except for inches should fall out, well, inches cubed, and then I'll take the cube root. So let's see, therefore C equals 16,206.394 divided by 6283.18. So C cubed is 2.579 inches cubed. C equals the cube root of that thing. Let's see, how does that work on this calculator? This. No. Let's see. I'm not sure how this calculator does cube roots. All right, let's do it that way. Sure. That could be right. 1.531 inches. And that's not the diameter though, remember that's the radius. So diameter is equal to C times 2. 3.062 inches. But that's assuming I actually did the cube root right, which maybe I did. Let's find out. Oops. So minimum diameter for what I drew as the green motor shaft, 3.062 inches. No, 2.742. So I could have done the cube root incorrectly though, because I don't know how to do it on this calculator. Let's go over to MathCAD, see if it'll help us out some. Let's get where you see MathCAD. Let's see. So what did I have? I had 4,000 psi. I had this. Oh, wanted that. Let's see. Wow, that's gigantic, isn't it? Where's the Can't even see the, there it is. Okay, there we go. All right, so let's see if we can get something out of this. 4,000 PSI equals 16,206 point, I think it was 394 inch-pounds. So that's T times C over pi 2 times C times all of that times C to the fourth. And then let's see if we can solve for that guy. We don't need the ones with the imaginary parts, so we'll take this one, which looks kind of crazy. And D equals C times 2 in inches, 2.743. So I just didn't know how to do a, it sounds weird, but the calculator I'm using, I don't know how to correctly make it do a cube root, just because I haven't used that particular calculator much, but there's the correct answer. So you do need to know how to make your particular calculator do a cube root. This isn't the one I normally use, so it's just the one I had laying around. All right. The next thing would be, and we won't need to do the whole next thing, but let's do the setup for the next thing. So let's go back over to here. So the next part is the minimum satisfactory diameter for the power shaft. So the yellow shaft. So the deal here is that you've got this gear ratio. And we already talked about the gear ratio. You can be given gear ratio by just directly given the ratio between these two gears is 5 to 1. You could be given, like you're given here, where you have the number of teeth on one gear and the number of teeth on the meshing gear, and you just divide one by the other. So 85 divided by 17 is 5. Or you could be given the sizes. So the 85 tooth gear is 5 inches diameter, and the other one is 1 inch diameter, and divide those. So one of those three ways, you'll have the ratio between the driving gear and the driven gear. And in this case, it's 5 to 1. And we already calculated the torque in the green shaft being that highlighted number there, 16,206.394 inch-pounds. And we already mentioned that the yellow shaft is spinning 5 times faster. So it's going 350 times 5 RPM, but its torque, so the torque in the power shaft equals the torque in the motor shaft divided by 5, that gear ratio. Oops, not ration, ratio. So for us, that would be 16,206.394 inch-pounds divided by 5. So whatever that number is, 16,206.394. 16,206.394, 3,241.279 inch-pounds. So that would be the torque in what I colored the yellow shaft here. So you would use that torque and do the exact same thing we just did here, where you have the 4,000 PSI maximum allowable stress in the shaft. You have a different torque, the torque that's 5 times less. C, where it's a new C, is C is the radius. The radius of the yellow shaft, the power shaft, pi over 2 times that radius to the 4th power, and solve for the radius, and you would get something you would think it would be thinner because, a smaller shaft because it has to deal with less torque. And torque is what is going to cause it to fail in shear or in angle of twist if it has too much angle of twist. So that's the process for doing that. And then the last part would be, all right, well, knowing that, what's the angle of twist between actually from one end of the yellow shaft to the other, ignoring the very ends that aren't twisting. So that would be finding the torque. Actually, the torque that we just talked about, the one that's 3,000, yeah, this one, that is the torque in this first section. All of that torque goes here. Some of that torque is removed from gear, delivered to whatever's connected to gear A, however you want to word that. They worded it with transmitted. That makes sense. And then the remaining torque will be in this last section here from gear A, between gear A and gear B. And you would have to figure out, well, if I delivered, there's 49 horsepower here, I have the speed it's going at, I can figure out the torque in that section. That'd be one way to do it. You could just use the ratios, 49 to 41, as the amount of torque that would be remaining if you wanted to work it that way. But you could do it multiple ways to figure out how much torque is remaining in that gear section from gear A to gear B. This one is probably a little more going on than what a test problem would have, just because it's got 3 different parts to it. But you can see where little individual pieces of this could be used in a test problem. I've opened up homework 18 and 19. Homework 20 is actually going to talk about a whole new topic. So this is the last torsional shaft type topic for the quarter. And the rest of the stuff, there's a couple more topics that are more, they don't really fit well into any other category. And so they get put at the end here. So there's a pressure vessel, some stress concentrations, and I think that's it. I think those are the only topics left. So there's not a lot of new topics left. Next week, we actually start the retake, if you need to retake exam 1 or exam 2. And then we have exam 3. You've got your final report due for the truss project. And so there's not too many new things that are going to be showing up from here on out. It's a lot of just finishing up the work that we've already started. All right, I will see y'all on Wednesday with some pressure vessel topic, another relatively short one. And then on Friday with stress concentrations by hand. We've kind of done that with the SolidWorks simulations, but you can also do a similar thing by hand and get a rough idea of the maximum stress if you suspect there's something higher than what we've been calculating. We've been calculating kind of the average stress, but there are reasons that we'll talk about that you might want to calculate a higher stress that exists at some notch or at a corner or something like that. So we'll do that this week, and then next week we'll work on our exams. I'll see y'all Wednesday.